Here is another interesting question that we want to look at. Suppose you have some kids, maybe, right? A son and a daughter, maybe, and then you invite their friends to come for a sleepover. Okay, so they come and stay for a night. So their friends arrive, and then there is total 10 kids, including their friends, right? The children and their friends together. There are 10 of them. Now, when there are 10 children, you cannot put them all into the same room, because the rooms are generally easy to accommodate 10 people. So they will say that, okay, we don't mind if you all want to put in one one room, but let us not do that. We will give you 3 rooms, and you must use the 3 rooms to sleep, right? So or let's say 4 rooms, right? In the question we are given 4 rooms. Okay, so we are given 4 rooms to the 10 children. Now say that, okay, you go to the 4 rooms, and then whichever groups you want, you can form, right? Who are want to sleep with others, decide, and then go and find the corresponding rooms, and then let us know, and then go to the rooms, right? Now, how many different ways this can happen, right? Because depending on the children's preference, right, whom to group with, there could be many possible ways to do this, right? So how many different possible ways this can happen? So how do you solve this, right? If you ask this, then there is something which is not very clear about this question, right? So what is not clear is that when we say how many different ways, what exactly do we mean? Because I can say that, okay, the children, let's say A, B, and C, are going to the room number 1, because I gave 4 different rooms, right? So room number 1 is not the same as them going to room number 2, right? Because rooms are distinct, right? If I consider the rooms are distinct, then they are not the same. But maybe if you don't consider the rooms, I gave you 4 rooms, doesn't matter. What matters is the way the children are grouped together, right? I want to just see that who are all going together to sleep, right? But if I also want to know who are all going to which room, then that is a different question. So there are 2 different questions one can bring from this. Now, both of them can be interesting questions, right? So therefore, we want to look at both of them, right? So what happens if when the which group of students or children go to which room is important, and what happens if the rooms are not considered different? That is, which group goes to which room is not important, but what kind of groups are formed is only the interesting part. Now, if you think about it, you can see that these 2 questions, even though can be very different, in their values, they are very related as well. Okay. So can you think of some argument to say that solving one is, like solving the other also, in some sense? So this is an easy observation, but I want you to think about this. Okay. So think about it, and tell me why solving one is as good as solving the other, right? Once you get an answer to the first one, you know how to solve the second one, or vice versa, right? So again, I don't want to give all these small whys, right, answers to all these small whys, because if you don't think about this, you are never going to learn things. So therefore, some of these questions, when I write just why and don't explain why, it should be something which, if you think about for some time, you should be able to come up with. It's not going to be a very difficult thing, but something interesting, and you should be able to come up with that argument. If you are not able to do that, then there is something that you have to work more. Okay. So hoping that you solve, let us continue. Now let us look at more general statement of what we were looking at. So let k less than or equal to n be positive integer. Okay, so n is a natural number again, and k is also a natural number. Now a partition of this set, let's say set 1 to n, right, into k blocks is a set of k subsets of the set 1 to n. Let's say B is equal to set B1, B2, etc. Bk, right, where Bi's are blocks, such that Bi intersection Bj, where I not equal to j, is empty, that they are disjoint, right, pairwise disjoint, and their union Bi is equal to the whole set, right, set 1 to n. So I think I already mentioned this notation that I will use, the notation that the within the square bracket n is the set 1 to n. Okay, 1, 2, 3, etc. n. Now, so what we have defined here is a partition of a set. Okay, so a set with n elements I am partitioning into k blocks, such that they are pairwise disjoint and the union is the whole set. And now we want to find the number of possible such partitions, right? Number of partitions of the number of partitions of the set n or 1 to n to the k blocks with this property is called a partition. Yeah. So we want to find out such a number of such partitions. Okay? So we want to count them. And if you just look at this definition, it will be very clear that the earlier question that we were looking at regarding the children sleepover party was precisely the same, right? In some case. Now here is an example. So if you take the set 1, 2, 3, 4, then you can partition this into 3 blocks, right? In 6 different ways. Okay? So I want to partition it into exactly 3 blocks. Now that can be done in 6 different ways. That is the claim. So let us look at the 6 sets that I am going to give and see whether they are the partitions first. So here is the set. Set 1, 2, set singleton 3 and singleton 4. That is the first partition. Then set 1, 3, singleton 2 and singleton 4, and etc. etc. Set 3, 4, singleton 1 and singleton 2. Right. So these 6, we can see that they are each blocks are disjoint in each of these partitions. Right. So if you take any of these, the elements does not repeat, and they form the all elements appear there, so therefore the union is the whole set. So these are all partitions, and we have exactly 3 blocks, right? A 2 element set and 2 singletons. And since we want 3 blocks and we have only 4 elements, the only way to partition is to have like 2 in one set and 1 and 1 in other sets. And this will tell you why we can only have 6 possibilities, right? So maybe you argue it slightly more formally, right? Why only 6 are there? So 6 are already there, but why there are no more, right? So give me an argument for that. Now, another example, but I want to do this as a kind of homework example, or maybe not. Maybe why don't we do it here? So there are 25 partitions of the set 1, 2, 3, 4, 5 into 3 blocks. So we said that when there are only 4, right? 1, 2, 3, 4, number of partitions into 3 blocks is only 6. Now when you add one more, we have 25 of them. Now how is this exactly 25? Can you give an argument why this is 25? Okay. So maybe you should stop and think about this. for some time before going further, because if you can do it on your own, that is the best. Okay? Now let me give an argument. If you have thought about it for some time, please continue. So we are looking at the partition of set 1, 2, 3, 4, 5, right? So there's exactly 5 elements. 1, 2, 3, 4, 5, right? Into 3 blocks. 3 blocks. Since we are looking at exactly 3 blocks, what we can observe is that the only possibilities are you can have elements, the sets, in the partition be of cardinality either 3, if there is 3, and since we need exactly 3 blocks, if you take 3 elements into one set, the other 2 must be 1, 1, because there is only 5 of them, right? So it should be like something like cardinality 3, 1, 1. This is not the set 3, 1, 1. This is not set 3, 1, 1. So we should have the blocks of cardinality 3, 1, 1. This is one possibility. Other possibility is that you have 2, one subset has 2 elements. Then, since there are only 2 more and we have 3 elements, so we need to have another 2 and then 1. And you cannot put 4 into 1. You cannot put 1, 1, 1, 1, 1, etc. because you are only allowed 3 blocks. So one can verify that the only 2 possibilities are blocks of size 3, 1, 1 or 2, 2, 1. Now, once you observe this, well, we know that since we have exactly 3 blocks, and you select the first, let's just concentrate on this part, right? 3, 1, 1, right? Suppose you select a 3 element subset from the 5 elements. So which means that how many ways you can do this? You can do it in 5 choose 3 possible ways, right? Once you choose the 5 choose 3 possible ways, so what is 5 choose 3? 5 into 4 into 3 by 1 into 2 into 3, which is 10, right? So in 10 possible ways, I select this. Then we have only choice is to take the remaining 2 elements as singletons, right? So there is 3 elements are already gone. The remaining 2 must be singletons, and there is no choice there. So we have exactly 10 possible ways to do this. Now, on the other hand, if you look at the 2 to 1 configuration, then you can see that if you choose, let us say, 2 of the elements, right? In the first, how many possible ways? 5 choose 2 possible ways, right? 5 choose 2 possible ways, you select the 2 elements, right? First 2 elements. Then to select the remaining 2 elements or 1 element, right? Once you choose 1 element, it is very clear what are the other 2 elements going to be. Or if you select the 2 elements again, it will be clear what is the remaining 1 element, right? So the remaining 2 elements can be chosen in how many ways? Another 5 choose 2 possible ways, right? I mean, not 5 choose 2. The remaining is 3 choose 2 possible ways, right? Then the last one, there is no choice. But there is a problem. If you use the product rule here, like 5 choose 2 and 3 choose 2, then what you will get is that 5 choose 2 is 10 and 3 choose 2 is 2 is equal to 30. But I claim that this is wrong. Why is this wrong? This is wrong because when we were doing the counting, we did some over counting. Can you think of why there is some over counting? Okay. So the reason there is an over counting is that when you selected the first two element subset in 5 choose 2 or 10 possible ways, and then you selected a 2 element subset from the remaining 3 elements, the 2 element subset that you selected in the first and the remaining 2 element subset you selected in the second could also appear as, those 2 elements were selected in the first choice and the other 2 elements were selected in the second choice. So in these two possible ways it can come, and we are counting both of them when you take the multiplication. So therefore, since we are counting each of these exactly twice, we can divide by 2. So we will get 10 into 3 divided by 2, which is equal to 15. So I have 15 possible ways only, not 30 possible ways. And therefore, the total number of such partitions into blocks is 15 plus 10. 15 plus 10 is equal to 25. Okay. So we need to be very careful when we do this kind of counting, because over counting must be avoided, right? Or if you do overcount, you have to find a suitable way to deal with that. Okay. Now, the number of partitions of an n element set into k blocks is denoted by S of n comma k. Okay. So these numbers that we are looking at, they have a specific notation. So if you are looking at n element set and you are looking at k blocks, then S of n comma k denotes the number of partitions of an n element set into k blocks. And this is called the Stirling number of second kind. Okay. So the number of partitions of a set into k blocks is denoted by SNK and is called the Stirling number of second kind. So one can ask, like, what happened to the first kind, right? Why we are not looking at the first kind before we look at the second kind? We will look at the first kind sometime in the future, but that is much more difficult to deal with. It's a much more involved computation, and we will look at those things in the later part of the course. So for the time being, we will stick with the Stirling number of the second kind. Now, how do you find SNK? Can you find a formula for SNK, or can you find a way to compute SNK? Right? These are some interesting questions one can ask. So I want you to think about these questions. And here are some observations. So SNK is 0 if k is greater than n, right? That is very clear. And Sn0 is 0 if n is greater than 0. That is also kind of clear why. And S of 0, 0 on the other hand is equal to 1, right? That is precisely one way to do this. Basically, there is nothing to do, right? So that is precisely the one way. Now, S of n comma 1 and S of n comma n are always going to be equal to 1. This is also another observation. You should verify that, whatever I claim, don't take it for granted, right? When I say something and you think that why it is that case, it means that you are supposed to figure it out yourself. Okay, think about this and find out why. And they are kind of easy questions. That's why I'm giving you it as an open, just a statement without any argument. Okay, so figure out why these things are the way I have defined it here. Now, to come up with solutions to this, we might need to use some new ideas. So one of the ideas that is called recursion. Okay. Now, suppose you are given a sequence of, let's say, unknown values, right? So let's say A1, A2, A3, etc. Right? Is given sequence of unknown values. Now, what we want to know is that we want to find out a way to find, or describe, let's say, an. Okay. So suppose I write an is equal to f of n, where the right hand side expression, okay, the right hand side expression does not, the right hand side expression does not depend on any of the AIs, but it depends on n, right? It can depend on n. Okay, so if n is equal to f of n, where the right hand side is an explicit formula without depending on any of the AIs, any of the unknowns, but it can depend on n, is called a closed formula for n. Okay, so it's a closed formula for n. Now, on the other hand, a formula of the form an is equal to f of, let's say, n comma a naught, a1, a2, etc., an minus 1. I mean, this can be something, other than an minus 1, but something less than n, of course. The index should be less than n. Together with some initial conditions like, a naught is something, a1 is something, etc. Some of these things can be already given, which are not defined recursively. They are given explicitly. Then such a statement is called a recursive formula for an. Okay? So an depends on some previously determined unknowns and n also, but it does not depend on anything that we have not come across so far, right? So such a description is called a recursive formula. Okay. So basically, if you know, right, the some of the initial values, you should be able to find the next one, right, which is not known. Then using that, you can find the next one, right, in a recursive manner. That's why it's called a recursive formula. So let us look at an example, right? So for let's say n greater than or equal to 0, let's define p subscript n, be the set of all subsets of the set 1 to n. And let us define an to be the cardinality of Pn. Okay. So this is something most familiar to you, right? So basically, you are looking at the power sets of the sets that we are talking about, right? Set of all subsets of 1 to n. So power sets of the set 1 to n. And we want to find out what are the cardinalities, right? We already know how to do it using the product rule we did long time back. But now we want to use and try to solve it using a recursive formula. So we will come up with a recursive formula and try to prove it, to solve it and get an answer. So for let us say solving something like this, what we can do? Well, what we can do is that we can do some observations, right? So we observe that a0 is equal to 1, right? Because a0 is the cardinality of p0, right? And p0 is the set of all subsets of the empty set, which is the set containing empty set. And its cardinality, because it is singleton, the cardinality is exactly 1. So a0 is 1. So we get an initial condition. Now we need to find the recursive relation. Okay. So to find the recursive relation, what we do is the following. Let me just erase this. So we do the following to find a recursive relation. So what is that? So given, let us say, given, let us say, n is greater than or equal to 1, to construct or to build any subset, let's say S in Pn, what we can do is the following. Okay, so to select such a subset, we will select the any subset, let's say S dash of the subset 1 to n minus 1, right? So we remove the element n and look at the set 1 to n minus 1. So look at the subsets in P n minus 1, right? So this means that S dash belongs to S dash not belongs to, S dash is a subset of the set 1 to etc. n minus 1, right? So S is some subset of 1 to n minus 1, and then we will select the element n and say that, okay, now I have two choices. One is either to add n to this set S dash to construct a subset of Pn, or I don't add it, I just keep it as it is, right? So there are these two choices. Either I add this element to that set or I keep the subset as it is. Now this way I can create all possible subsets of Pn, because I take all the subsets of 1 to n minus 1 and then I add n or I don't add n, right? So I will get all possible subsets this way. So there are two choices. Either add n to S dash or not add n to S dash. Okay. So now, once you know this, using the product rule, we can we can figure out that an is equal to 2 into an minus 1, because whatever is the number of elements in in Pn minus 1, we are doubling it, right? Because I take these guys, any element here, I add n or I don't add n. Both way I get a subset of Pn, and therefore I get 2 times of this many, which is 2 times an minus 1. So for any n greater than or equal to 1, we have an is equal to 2 times an minus 1. Now with the initial condition that we figured out, that is a0 is equal to 1, we can now try to find out the values of an, right, as follows, right? A0 is equal to 1, therefore a1 is equal to 1 into 2, which is 2, then a2 is equal to 2 into 2, which is 4, then you get 8, 16, etc. for a3, a4, etc. So we find out what are these numbers. So now from this we can guess, right? We can guess the value of an, right? We see that an is something like 2 raised to n, right? N is 2 raised to n. And then once we find the guess, we verify this and we can use induction to prove it actually. So how do we do that? So we do the following, right? We guess that n is equal to 2 raised to n, and to prove we use induction. So the base case is n is equal to 0. A0 is, we already know that it is 1, which is 2 raised to 0 also. So therefore that is okay. Base case is fine. Now we take the case n is equal to 2 into an minus 1. And by induction hypothesis, for an minus 1, it is 2 raised to n minus 1. And therefore this is equal to 2 into 2 raised to n minus 1. But that is equal to 2 raised to n, right? So therefore n is equal to 2 raised to n, which proves our hypothesis. Therefore we have the proof, right? So therefore by induction we get that n is equal to 2 raised to n. So if you can guess what is the closed formula for an, most often we can use induction easily, because we know, like a1, even though it may depend on a1, a2, etc., an minus 1. Since we know that each of them has the same formula, we substitute that and then try to figure out why the recursive relation must satisfy this. And if it satisfies, then we get that it is indeed the case. So this way we have proved it. Now, homework. This is a question that I want you to think very thoroughly about. It's a very interesting question. Okay, and this question has been solved in, by the Indian mathematicians many years before, and so you should be able to thousands of years before, in fact. So I want you to think about this and try to see how you will solve this and how you form a recurrence relation for this, for example, right? So here is the question. So in a certain type of poetry in Indian languages like Malayalam, Sanskrit poetry, the syllables of length 1 and length 2 are allowed, right? So each letter can be either short or long, right? Right? Ka, etc. Right? So we have this long and short syllables. We will say that Lagu, the short one, and Guru, the long one. The long one has exactly twice the length of the short one, and that is a long accepted convention, right? The long one is a and are exactly the second one is twice the length of the first one. It's supposed to be like that. Even though we don't do it precisely when we talk, it should be exactly like that. So the syllables of length 1 and 2 are allowed. Now, the total length of each line in the poem is fixed to be a positive integer, in terms of the syllable length, right? It should be exactly the same, right, from certain kind of poetry. So we'll say that, okay, we will allow exactly, let's say, length 5, right? Syllable, whatever you use, it should be of length 5. So you can have maybe 5 lagus, right? 5, lagu, right? Right? So there are 5 of them. Or you can have maybe 2 and 1, 1, 1, or 1, 2, 1, 1, right? Or 2, 2, 1, etc. All these possible lengths are allowed, right? So, once the length of each line is predefined, something like this, this kind of a pattern we can decide. So once you decide a pattern, that such a pattern is called a meter, right? For example, LLG is a meter with length 4 because LL 1 1 and G has 2, right? Guru has 2, Lagu has 1. So 1 1 2, it has length 4. And GLG has length 5 because it is 2 1 2, right? Length 2, Guru has length 2, then Lagu has 1 and again 2. So formulate a recursive formula to count Fn, where Fn is the number of different meters of length n. Okay, so some formula, define F0, F1, etc. You find some initial conditions and write a recursive formula to define Fn. And then if you can solve the recursive formula, well, even better. But at the moment, I want you to come up with a recursive formula for this. So this is what I want you to do. Now, before we finish today, let me state a theorem and you think about the proof. So the theorem is the following: for all positive integers k greater than or equal to n, the Stirling number of second kind S of nk is equal to S of n minus 1 k minus 1 plus k into S of n minus 1 comma k. So it satisfies this identity. Right? For every n comma k where k is greater than or equal to n, S of n comma k is equal to S of n minus 1 comma k minus 1 plus k into S of n minus 1 comma k. So can you find an argument why this is the recursive formula for Snk? So this is the recursive formula definition for Snk. Right? It depends on S of n minus 1 k minus 1 and S of n minus 1 k, and recursively it can depend on the previous ones, right? Basically. So this is what I want you to do. Okay, so think about how to do this. And we stop for today. We will continue with the proof of this and other results in the next lectures.